Hello everyone, so my name is Zammit. 3 weeks ago I submitted my PhD thesis, so I'm quite excited to be here. Thanks for the opportunity to let me speak and summarise my PhD. So during my PhD I developed the convergent close coupling CCC method for molecules. So you guys may have heard about it for its application to atoms, particularly in the last talk. And so I'll talk about our results, which were on convergent calculations of positron scattering from the H2 molecule and electron scattering from H2+. And my supervisors are Dimitri Fursa and Igor Bray, and we're based at Curtin University in Perth, Western Australia. We're down there in Australia, and as you may know, the next Icpeac is in Cairns, around there. Okay, so the motivation of my talk today comes from the Journal of Physical Review A and the International Atomic Energy Agency. And they've both stressed the importance of assigning uncertainty estimates on theoretical collision data. And these uncertainty estimates will allow plasma modelers to basically trace their accuracy in their models. So they'll be able to concentrate on the accuracy in their models and not the accuracy of their input data. So that's the idea. One might ask, how do you actually assign uncertainty estimates on theoretical collision data? Well, a powerful method that we use is performing convergent studies. So increasing the size of our calculation and seeing how our results vary. And we say we achieve convergent results when our results don't vary that much, within 1 or 2%, and that's when we know that we've got the right answer, and we say that our results are accurate within 5% or less. And so, as far as we are aware, no one has actually demonstrated convergent results in electron molecule or positron molecule scattering. So here I'd like to demonstrate this for the first time, the positron scattering from H2 and electron scattering from H2+. Okay, so we use the convergent close coupling CCC method. And what we do is we expand the fixed nuclei total scattering wave function in a close coupling expansion here. We transform the body frame electronic Schrödinger equation to the momentum space limit Stringer equation for the T matrix. And we expand this three-dimensional T matrix with a projectile partial wave expansion and solve it in effectively one dimension. So once we obtain our T matrix elements, we can calculate our cross-sections, and we utilise a analytic form subtraction method to top out our cross-sections for large values of orbital angular momentum. So if we want to get accurate cross-sections, we need an accurate T and also a converged expansion of the total scattering wave function. So we need to have convergence in our close coupling target state expansion with respect to the number of target states that we take. We also need to make sure that we have convergence in our projectile partial wave expansion, which comes in here for our T. So this is the maximum orbital angular momentum of our projectile partial wave expansion, Lmax, and Mmax is the maximum orbital angular projection of the partial wave expansion. And it also tells us when we obtain cross-sections from the T matrix elements, or we start using Born cross-sections to complete the expansion. Okay, so we'll start with positron scattering from H2. Here we utilise a single centre expansion method, which implicitly includes positronium formation via positive energy pseudostates. So these positive energy pseudostates represent a unbound electron from the target, which can correspond to either positronium formation or direct ionization. Unfortunately, this method gives unreliable results between the positronium formation and direct ionization thresholds, and this is because the target electron can be unbound from the target in this 6.8 energy region. So this causes a mismatch in boundary conditions, so we won't present results in that energy region. A careful thing to note is that in these single centre expansion methods, we require a large partial wave expansion of the positron-electron potential. So this is to take care of the strong electron-positron correlations, and these large partial waves are constructed from target state orbitals which have large orbital angular momentum. The advantage of this method is that it's numerically stable and relatively simple to implement compared to a two-center post-coupling expansion. Okay, so the first thing we want to do is describe our target state. So we diagonalize our electronic Hamiltonian in a single-center Laguerre basis expansion, and we utilize this coordinate system, or we choose this coordinate system, where our two nuclei are separated at a distance r from each other. The midpoint is set halfway between the two, and this is in the body frame, so the internuclear axis is along the z-axis. So as I said, it's a single center expansion method, so we need to be a bit clever about the way that we go about describing our target, or the method that we use to obtain an accurate structure model. Okay, so the first thing that we do, we perform a two-step structure calculation. What we do is we diagonalize the electronic H2 plus Hamiltonian with a large Laguerre basis, and we generate an accurate 1s sigma g state, the ground state, and we save that. The second thing we want to do is diagonalize the electronic H2 Hamiltonian, and we do this with a smaller size Laguerre basis, which has 17 minus L functions, where L is our orbital angular momentum, up to L equals to 7, so that means 17s, 16p, 15d, so on, and our n equals to 10 for the orbital angular momentum equal to 8. So our basis has a maximum orbital angular momentum equal to 8. These are used then to construct atomic orbitals in a basis. We then replace our 1s sigma g atomic orbital with the accurate 1s sigma g target state we generated in the first step, and then we construct two electron configurations, diagonalize our electronic Hamiltonian, and we get our structure model, which is 1013 states used in our scattering calculation. So how accurate is this method? Well, we compare with some accurate calculations given in bold for target state energies at the equilibrium distance. Our 1013 state model is indicated by CCC, and this is static dipole polarizability for the ground state. And as you can see, we do quite good. And we even surpass the molecular R matrix with pseudo-states method, which uses a Gaussian basis and performs multi-center expansions. So we've actually got a sufficiently structured model to produce quality collision data. Okay, so now we'll look at how accurate our scattering calculations are. So we look at convergence with respect to the target state expansion. So we perform three calculations. Our largest one that we just described was 1013 states. We compare it with a smaller calculation, which uses Lmax equals to 6. So seeing if we have convergence in the orbital angular momentum of our basis to describe our positron electron potential. And then we also compare it with a smaller basis, which has less basis functions per symmetry of L. And our results are within 1% of each other, so they converge, both in NL and Lmax, so orbital angular momentum and the number of basis functions. So now we look at our projectile partial wave expansion, so maximum orbital angular momentum Lmax equal to 7, and our maximum orbital angular projection also equal to 7, through to equals to 9, and these results are within 1.5% of each other across the entire energy range. So we've achieved convergence in our projectile partial wave expansion and our close coupling expansion. So these results should be converged. And this is a further demonstration of our convergence. So these 550 state calculations were preliminary results which we've already published, and we compare these at the equilibrium distance. And by the way, this is the grand total cross-section, sorry. And our results are right on top of those. And these are completely different structure models, scattering calculations, and they're right on top of each other. So now we'll look at the scattering length, so actually seeing if we've taken into account virtual positronium formation accurately. So we perform scattering calculations at near zero EV, and we obtain a flat cross-section. From there we can extract the scattering length, and we compare with the accurate calculations of Zammit and Mitroy at the mean internuclear distance, and we're within 3%. Recently, FETIS derived the scattering lengths of these experiments, and they're also within pretty good agreement. So we're quite confident that we've taken into account virtual positron information. So now comparing our scattering length as a function of the internuclear distance with Zhang and Mitroy again, and we've got great agreement up to r equals to 2.2, and we wanted to see, can we actually perform adiabatic nuclei calculations with this same scattering calculation? So this is all one scattering calculation model. So we plotted the probability density functions for the ground state, which has just got the one peak, and the first vibration excited state, which has got the two peaks, and they fit within this r equals to 2.2, I think. And this is the adiabatic nuclei cross-sections, and this is the probability density functions of the vibrational wave function. So we could do accurate calculations for scattering from the vibrational ground state and first vibration excited state. So lots of people in the literature perform calculations at the equilibrium internuclear distance, so I wanted to see how accurate that is. So we performed adiabatic nuclei calculations of the ground state, compared it with the equilibrium distance and the mean internuclear distance of the vibrational ground state. And you can see that the equilibrium distance has a difference of between 5 to 15% in the low energy region. So theorists, when you perform your calculations, it's careful to take these things into account, and it's probably, or it's a better approximation to use the mean vibrational ground state internuclear distance. Okay, so now we had a look at scattering from the vibrationally excited state in the low energy region, and we see between 20 to 30%, so this might be important in transport models, so if anybody wants this data or wants me to calculate more, let me know. So now comparing with other theories in the low energy region, so there's a whole bunch of theories which calculate this process. Most of them use certain types of polarization potentials. We just included these three here. And we also compare with other close coupling calculations, the molecular R matrix with pseudostates calculation and Schwinger multi-channel calculation. And they are about 20 to 30% lower than our results. And this comes from two things. One, they use the equilibrium internuclear distance, but they also perform a smaller close coupling calculation compared to ours, so they're not fully converged in their close coupling calculation. So taking our converged results and comparing with experiment, there's a whole range of experiments that vary quite significantly, so we can't agree with them all, unfortunately. This difference in the experiments usually comes from the different angular resolution, where generally the higher the measurements have better angular resolution. However, we're in very good agreement with the measurements of powers and their reanalyzed data like that is. Okay, so above the ionization threshold, direct ionization threshold, we're in excellent agreement with all experiments. And this means that we've accurately modeled positronium formation, which is one of the major scattering processes at the peak of the cross-section. Okay, so now we move on to elastic scattering, the differential cross-section of positron from H2, and this is the recent measurements of the AMU people. Here we don't have agreement, and this is also reflected in the grand total cross-section, where their results are about 30% higher than ours. Okay, so now we'll look at total ionization cross-sections of H2. So this is the sum of direct ionization cross-sections and positronium formation cross-sections. And here is the preliminary results which we published. And these results were converged in the orbital angular momentum, but we didn't check that they were converged in the number of basis functions for each of those symmetries. So comparing with our more recent results, we see that there's a sharper rise just above threshold, and this comes from more positive energy pseudostates being able to capture the positronium formation and direct ionization flux. And there's also a difference across the entire energy range. And this is from the 556 state calculation only having 10 negative energy states, while this one here, the large one, has 57 negative energy states. So the larger calculation is able to capture all the flux which is distributed to the discrete spectrum. And you can see that we have better agreement with the direct ionization measurements in the high energy regions for our larger calculation, which indicates we've got a better structure. And although it's not shown, the experiment of Bromley has a uncertainty in the impact energy of around 5 to 10 eV, so we're in quite good agreement with the measurements. Okay, so these preliminary results were published here, and we're currently working on a larger paper to describe all the theory and give details of these calculations. So now we'll move on to electron scattering from H2+. And again, we'll start off with the target description. We use the same sort of method again. So we use a two-step configuration interaction method, where here we get accurate target states for the 1s sigma g and 2p sigma u states. The largest calculations we use have a basis of 17 minus L functions up to L max equals to 4, and then we replace those 1s sigma g and 2p sigma u orbitals with the accurate target states in the first step, and then diagonalize, and we get 351 states for our scattering calculation. And I've got a bit of time, so this is how our structure compares with accurate calculations for energies, oscillator strengths, and static dipole polarizability. So again, we've got a good quality structure model. Now we look at convergence of these scattering calculations. So here is the 351 state model, which I just described, and we compare it again to two smaller calculations, so looking at convergence of the close coupling expansion. Here we've got smaller orbital angular momentum in our basis, and here we've got fewest number of basis functions per orbital angular momentum. And we look at the proton production cross-section, which is the sum of these two processes, dissociative excitation and dissociative ionization, which is the top panel, and all of these are right on top of each other, and dissociative ionization. So we've got convergence in our close coupling expansion. Now we look at convergence of our projectile partial wave expansion. We compare our results with Pinzola. So to do that, we actually had to use a unitized Coulomb-Born approximation to top up our results. And the equivalent size calculation as Pinzola used L max equals to 5, M max equals to 2 partial wave expansion, and our results are right on top of theirs, which is quite nice, but they're not fully converged. So we increase our calculation size and see that we get convergence by L and M equals to 9, and there's about a 15% difference between these two results. Okay, so now we want to compare with experiment. So H2 plus is produced by electron impact ionization of H2, which produces H2 plus in a range of vibration excited states. So most of these measurements take measurements of H2 plus in a vibration excited state. So we need to perform scattering calculations from each of these vibration excited states and weight according to their Frank-Condon factors, which is given by this dashed curve. And this is, by the way, was taken from the paper by El Ghazali, who measured their vibrational distribution. So this is the potential energy curve of H2+, the ground state and first electronic excited state. And we calculate scattering from each vibrational state with the adiabatic nuclei calculation here, and weight according to the vibrational distribution with this equation here. And because we're using a single center expansion method, our structure model is not accurate for larger values of the internuclear distance. And so what we used is an extrapolation technique to extrapolate our cross-sections as a function of the internuclear distance, and then we weighted and took into account those higher lying vibrationally excited states, which you can see don't account for much of the distribution. So we were able to fit the V equals to 10 vibration excited state within that region. Okay, so comparing with experiment for the dissociative ionization cross-section, first we'll look at our fixed nuclei calculations and see that they don't have much of a difference compared to our vibrationally weighted results, which means that there's not a huge dependence upon the vibrational distribution for the dissociative ionization cross-section. Our excellent agreement with the experiment of Pert and Dolder, and they do disagree with the experiments of El-Ghazali, and this is because the experiment of El-Ghazali measured fast energy protons arising from a Coulomb explosion, and assumed that that was because of the dissociative ionization process. Then what they did is they extrapolated that over the kinetic energy release of their protons arriving at detectors and said, okay, that's dissociative ionization. So they probably had some mixing of signals from the dissociative excitation process. I've got to admit that these experiments are quite hard to do, by the way, so that's probably where the error arises from. Whilst the measurements of Pert and Dolder measured protons arriving at detectors in coincidence, which is what you'd expect from a Coulomb explosion. So we're quite confident in those results. Now onto proton production. So proton production again is the sum of dissociative excitation and dissociative ionization. And again, our fixed nuclei results are around 4 or 5 times lower than our vibration weighted results, which means that the vibrational distribution is very sensitive. So the dissociative excitation cross-section is very sensitive to the vibrational distribution. In the high energy region, we're in excellent agreement with all experiments and also with the first order calculations of peak. In the intermediate energy region, we're again in good agreement with experiment. However, our agreement with the first order calculations of peak start to disagree, which is what we'd expect from the first order method. And then in the low energy region, there's a large discrepancies between experiments, and that's from the different vibrational populations which they have in their experiment. And we are in quite good agreement with Dunst. Okay, so these results were published here. And if you need any more details, you can ask me. Okay, so conclusion. So we developed a general approach for electron and positron molecule scattering using the CCC method. This is the first ever shown method to describe positron scattering across a broader energy range, and we achieved convergent results. So this method is looking very promising at the moment. And so for future research, I'd like to study heavy diatomic molecules, which are well represented within the single center expansion method, and polyatomic molecules, etc. And they're mostly like hydrides with a heavy center, and then lighter molecules on the outside, like H2O, methane, and OH, and things like that. And some future research for everybody in the audience. So if you're a theoretician, it's about time we all start assigning accuracy estimates onto our theoretical collision data. And we should also start using a fixed nuclei approximation that uses the mean internuclear distance instead of just the equilibrium internuclear distance. And this was first pointed out by Monod. It's emphasized by Zhang and Mitroy in this paper here, and they give a bit of a mathematical proof which you can go through. It's quite simple. Okay, I'd like to thank my supervisors a lot for their support over the last few years. Dimitri Verser and Igor Bray, and all the members at Kent University. They've all helped me at some stage or another. Kent University and the Australian Government for support, and CAMS for a great research environment, and all the calculations were done at the Pawsey Centre National Computing Infrastructure. And also to my parents who have also come all the way from Australia to come see me talk today. So that was quite a nice surprise, and thank you very much for listening to me.